Okay, so we worked this problem in another example, basically a Kirchhoff's loop rule example, but now I'm going to show you a different way. It's called the nodal method. And the nodal method just basically allows you to basically treat each individual node, i.e. any wire that goes from one junction to another is a node. So there's one, and there's one. Now the problem with this is it actually introduces a fourth variable in this particular circuit, one additional variable basically, but it does so in such a way that the algebra that has to be done makes life a lot simpler. So what we do with the nodal method is we, one, arbitrarily call some point the ground. And this is just like in potential energy where you were allowed to assume the potential energy was zero anywhere you wanted. And as long as you stuck to that, the problem worked out. So I'm going to put the ground right there. That means this voltage right here is what I'm going to call VC. So that's the voltage at the top. We have no idea what it is. It could be positive, it could be negative, it doesn't matter. But the big thing is we're going to get an equation for each of these nodes, one here, one here, one here, that'll have two variables, VC and the current in this node, VC and the current I2 in this node, and VC and the current I3 in this node. So by doing that, you can actually solve for the individual currents. Now, we know these are the answers from the previous example, or the example where I did this another way with Kirchhoff's loop rules. So I know those are the examples, so you can immediately see whether or not you got the results correct, because we've already checked these, even though despite the errors I made on the other example. But here's how it works. What you do is you start off at this arbitrary point that you called VC, which is one of the junctions, okay, at the end of a node. And you say, all right, well, here's equation one. The voltage VC is what you have there. But then as you go this way, I go from a negative terminal to a positive terminal of a battery. So that means my voltage increases by 90 volts. And I'll drop these volts and ohms and stuff later. And then since I'm going the direction of the current, see I1 goes this way in my diagram, then I know it's going to decrease. The resistor is going to cause a voltage decrease of 1 ohm times I1 plus 20 ohms times I1. And then my final result will be 0. So I'm just going to write this as minus 21 ohms times I1. So now I should have a voltage equal to 0 because I'm now at the ground. So I just set that equal to 0. So that's pretty straightforward. And the way we use this equation is we solve it for I1. That tells us that I1 should actually equal VC plus 90 over 21. I'm going to call that equation 1 prime because that's the one we're actually going to use. Now I'm going to do the center node, and I'm going to do it the exact same way. Here's equation 2. I'm going to say we started at voltage VC. Now I'm going against the direction of the current now, so going across this resistor is a voltage increase, and there's a 40 ohm times I2 and a 1 ohm times I2, so I'm going to call that plus 41 ohms times I2. But now I'm going from the positive terminal of a battery to the negative terminal, so that's a voltage drop of 45 volts. And I'm back to the ground spot, so that's all equal to 0. And this tells me that 2 prime is in fact equal to 45. Notice I'm going to drop the units here just like I did over there. 45 minus VC over 41 is equal to I2. So that's equation 2 prime. Again, that's the one we're going to use. And then finally, equation 3. I'm going to take this node over here, which is really odd because it doesn't have a battery. So you're going to see some weird stuff going on here. But basically, I start off with a voltage VC. But now I'm going the opposite direction of the current. So this is a voltage increase. And that increase is 30 times I3 or 30 ohms times I3. So I'll say plus 30 ohms times I3. And now I'm all the way back to 0 again. So I say equal 0. So this equation, oddly enough, is going to become I3 is equal to negative VC over 30. Now, we do know from the previous way we solved this problem that all the currents directions were chosen correctly because they all came out positive. So that immediately tells us that the VC is actually going to be a negative voltage. So that's kind of neat. We can watch out for that. That's also a nice little check when we go to do our algebra. If we make any mistakes and end up getting a VC that's positive, we'll immediately know our answer's wrong. Okay, so that's 3 equations, and since we introduced the VC, our unknowns are VC, I1, I2, and I3, so there's 4 unknowns, so we need 4 equations. The good news is Kirchoff's junction rule is still what applies, and that's the backbone of this whole nodal method, which, by the way, just in case you're wondering what I'm saying, it's called nodal method. So this way actually just takes the algebra problem out of it. You might have to deal with big numbers, but the randomness of how to solve a system of 3 or 4 equations and 3 or 4 unknowns is just taken completely out. So equation 4 is going to be Kirchoff's junction rule for that spot right there. If you see, it's I2 and I3 going in. So I2 plus I3 is equal to, and I1's going out, so that's equal to I1. So now that I've got I2, I3, and I1, I just plug those in and automatically everything works out. So I2, we know, is going to be 45 minus VC over 41 plus I3, which is minus VC over 30, is equal to I1, which is VC plus 90 over 21. Now what I used there was 1 prime, 2 prime, and 3 prime. I just basically plugged them into that, and that gave me these expressions. Now this seems really ugly, but in reality, if you remember how to deal with fractions with uncommon denominators, you just multiply it by the least common denominator. In this case, 41 and 21 are sort of, they're going to ruin everything for us trying to find the least common denominator. So we're just going to multiply all 3. So what I'm going to do is I'm going to take and multiply both sides of the equation by 41 times 30 times 21. And this one times 41 times 30 times 21. Now, what you see is when this multiplies by this first term, the 41 cancels out, so I just get 30 times 21. When this multiplies by this one, the 30 gets canceled out, so I just multiply 41 by 21. And when I multiply on this side, the 21 gets canceled out, so I just multiply by 41 by 30. So I really don't ever need to know what 41 times 30 times 21 is, but I do need to know the subparts of that: 41 times 30, or 41 times 21, or 30 times 21, so on and so forth. Good news is that math is pretty easy. It's just straight multiplication. So when I multiply these, what I ultimately get is this 41 times 30 has to be actually multiplied by 45 minus VC. So it turns out 41 times 30, you can probably figure this out for yourself. 30 times 21, you can figure this out for yourself, is actually 630. So I'm going to write 630. I don't know why I switched to red. I wanted a red just for that. But anyways, 630 times 45 minus VC is one expression, because that's, again, 30 times 21, the 41's canceled out. Now I have a minus, because that symbol right there, the 30 is going to cancel out, and I multiply 41 times 21. Well, 40 times 20 is obviously 800. And then you get 20 times 1, that's 820, and 40 times 1, that's 860, and then 1 times 1, that's 861. So now I say negative 861 times VC, because again, the 30 canceled out. So that's times VC. That takes care of this distributing to this whole term and this distributing to this whole term. Now I put the equals. Now in this case, the 21 cancels out, and I get 41 times 30. Well, 41 times 3 would just be 123. So this is 1,230. So I'll say 1230 times VC plus 90. Easy peasy. Now I distribute all that junk, and it gets a little uglier now. You're multiplying 630 times 45 and 1,230 times 90. I've done all the math for you. No big deal. We're just going to work it out brute force. So what I get when I multiply 630 times 45 is 28,350. So 28,350. Again, pause the video if you need to verify that. 630 times negative VC would be negative 630 VC. So that's taking care of this one and this one. Now I've got negative 861 times VC. So that's taking care of that term as well. Equals 1,230 VC. That takes care of that one. And now I have to do 1,230 times 90. And that gets a little uglier, but it's just 110,700. So it'll be plus 110,700. So that's it. Notice this equation. This is the whole beauty of the nodal method. By having each node only have two unknowns, the VC and then the current for that one, we automatically get a really easy system to solve for VC. Once we have VC, we go back and plug that into the individual currents, and that gives us our currents. And the benefit is we get the voltage at a particular spot too that we didn't necessarily ask for. So now what I'm going to do is put all the VCs on the right and put all the regular numbers on the left. So it's going to be 1,230 plus 861. Notice when it comes over, it'll become positive, plus 630. All of that times VC is equal to 28,350. And that's going to be minus 110,700. The focus might be getting a little bit off. Let me work on that. Okay, yeah, that still looks pretty good. Okay, so it turns out when you add 1,230, 861, and 630, you actually get 2,721. And when you subtract 110,700 from 28,350, you end up getting negative 82,350. So that gives us VC is actually going to be equal to negative 82350 over 2,721, which equals negative 30.26 volts. So VC is equal to negative 30.3 volts. Again, I'm pretending like I did when I did the example before that all the numbers are 3 sig figs, and ignoring the fact that, you know, adding two numbers to two different number of decimal places gives you a different sig fig rule than the sig figs. I'm just pretending like everything I want to keep 4 sig figs for are like 2 decimal places when we're adding, just to be safe. And then when it's all said and done, I'm just going to pretend like we round everything to 3 sig figs, and that'll be close enough to the proper number of sig figs. Again, this is really horrible sig fig work, but we're just making it quick and easy. So now that we have VC, we can go through with equations 1 prime, 2 prime, and 3 prime to actually find out what I1, I2, and I3 are. So I1 is just going to be equal to, notice it is VC plus 90, so that's negative 30.26 volts plus 90, all that divided by 21. And it turns out that that gives me 2.845 amps. So I'm going to say I1 is equal to 2.85 amps. Now using 2 prime, this is from 1 prime. Using 2 prime, I'm going to say that I2 is equal to 45 minus VC over 41, which is 45 minus a negative 30.26. I had to track that down for like 20 minutes to realize what I did wrong there. If you forget to put the negative in there, it's going to definitely give you the wrong answer. So be careful with that. That gives me a current I2 that's actually equal to 1.838 amps, or 1.836, excuse me, amps. Okay. So I2 is actually going to be equal to 1.84, which again is what we had before. Now finally we can use 3 prime and see that I3, which is supposed to equal negative VC over 30, that becomes negative of negative 30.26 over 30, which gives us the wonderful number that we expected, 1.009, which is even rounded to the right number of sig figs, or is even carries out to the same digits that we had the other way we did it. So we get I3 is equal to 1.01 amps. Again, exactly the same results we had the first time. So that's the nodal method. It works really wonderful, especially when you have circuits where you've got distinct nodes that don't break up into other nodes or don't have other nodes connected to it. It gets ugly if you have, circuits that look like this, this, and this, but then has another break-off point. Oh, sorry, missed that. So it gets ugly if you have this is like the circuit we had before. So there'd be resistors and batteries on here, resistors and batteries on here, and resistors and batteries on here. But if you have something weird going like this, or some little thing going like that, the nodal method gets quite ugly, because you have to do that's a node, that's a node, that's a node, actually that's a node, and then that's a node, and then this is a node, and this is a node, and then this is a node from here to here, and it gets really ugly. So the nodal method is not great for that, but these types of ones, it's pretty straightforward. So hopefully this method will help you solve these problems a little more trivially. That's it.